So this video is going to be about this little atlas that I made for the ARM architecture called the ARM Machinists Atlas, which is based off the version 7 A&R edition of the manual. I'm just going to be describing what this is, how to use it. It's a visual representation of all of the ARM instructions in binary according to the manual. And it's color-coded, and because ARM's really cool and categorical with its instructions, I break it down that way visually as well. Or I do my best in an infographic, I guess. So in this case, I'll kind of zoom in because this is incredibly illegible. And I should say, it's also broken down into the conditional and unconditional instructions. The top half is conditional, the bottom half is unconditional. So I'll zoom in a bit so you kind of see this a little bit better. In this case, you see, at the top level of this tree, we have our conditional instructions. And then it's categorized by those two bits there after the condition field, the op1, and then another bit towards the end there. We'll define what the next kind of category of instructions that they're going to be. I mean, they're all going to be conditional instructions, but let's follow this yellow line to one of the subcategories here. We have the data processing and miscellaneous instructions. So in this case, they will all start with 0, 0. So we had that op1. This 0, 0 defines these are the data processing and miscellaneous instructions. And then this can be further subdivided based on the bits that we put in these green fields as well. So we're going to follow this yellow line kind of all the way over to the edge here, and we have our data processing instructions for the register format of them. And all of these instructions will be defined with a 0, 0, 0 in machine code. And that means if it has a 0, 0, 0 there, they will all be data processing register instructions. In this case, if you scroll down all these instructions, you notice they all kind of have the same format here. And the instruction itself, if we zoom in a little more, is defined by this next field of machine instructions. So in this case, a 0, 0, 0, 0 defines this as being an AND instruction. For here, 0, 1, 0, 0, that makes this an add instruction. And the next field is this S bit. This just defines if we want the flags that are a side effect of the instruction to be set or not. If you make it a 0, it doesn't even set the flags. Is really what that means. And then, say we're doing an add. What this really means is, we have a destination register and we're adding RN and RM. For the most part, without going into the other fields. That's just kind of a breakdown of, if you want to set these bits, this is kind of a guide to knowing which bits to set in order to do an instruction in pure binary. And then I also got a helpful kind of guide on what registers to, what ones and zeros to put for making a register. If I go all the way over here, down here we have our legend. So in this case, RN, RD, RM, all those fields. These ones and zeros in purple here define what register it's going to be. R0 through R9 and all the rest ones like FP, IP, all the way down to PC. And also, if you want to know what condition you want your instruction to be, because in ARM, almost all the instructions can be conditional, which is kind of cool. This is kind of a guide for what you do to make the ones and zeros to define what condition you want it to be. In most cases, it's going to be 1, 1, 1, 0 for no condition, and that just means run the instruction. There's no conditions for it. Not the same as unconditional instructions. It's a different thing, actually. But, if you wanted to have instructions to be conditional, like equal, not equal, greater than, less than, you got all those right there. So that's that in a nutshell. That's the guide right here. So now we're going to talk about actually using it. What our goal in this video is going to be is to write hello world, but in binary, not assembly, but in binary. Now, I say not assembly, we are going to use an assembler, and we are going to take some shortcuts, like we have our string of hello world. We're going to type the string of hello world out in a normal, sane human way. But what I mean is everything else that's assembly, the actual instructions that do the things, we're not going to use assembly. We're going to write it purely in binary because we have this atlas as a guide, which is kind of the point of why I made this beyond just the artful nature of it. So in this case, hello world is simple enough to use in this example. We don't want to get too complicated, obviously, for writing a program in straight binary. But it's simpler than it sounds. I mean, really, all we need to do is being that I'm on a Raspberry Pi, which is Linux, we're going to do syscalls. We're going to use instructions to set up values we need to do to make the syscalls to do the things we want to do. In this case, we only really need to do two things. Really, mainly one thing, which is write to the screen. And then secondarily, we do need to exit the program gracefully. Those are the really only two things we need to do. The more complicated one is writing to the screen, but it's not that bad when you break it down. In this case, if you want to know what this looks like to Linux, this is kind of what it should look like if you want to do it in C. But we have 3 arguments for writing to the screen. I mean, in this case, the screen, we're having to define that as well. The file descriptor here, that's the first argument. We're going to set that to 1, which is standard out. The next argument here is the buffer. This is just a pointer to where the string is. So we need to have an address of where our string is located. In this case, that's going to be the most complicated thing we're going to do, but it's not too terrible. And then a count for how large the string is going to be, the amount of characters that's going to be in the string, including a new line. We need this because this kind of a string is not null terminated, where the null actually tells you where the string ends. We don't have that here, so we have to have some way to define it, and this is how it's handled with the write syscall. So that's that. And to be more clear on where we put the arguments and how to handle that, what order they come in, I mean, I should say this table here is based on x86. It doesn't matter. I mean, in this case, just replace EAX with R7, the R7 register, which is the argument for what kind of syscall we're going to do always goes into R7. And then the next arguments in the order that we saw in that man page, the arguments, you know, from left to right are registers R1, I mean R0, R1, R2, R3, and so on. So instead of EBX, it's R0. Instead of ECX, it's R1. Instead of EDX, it's R2. That's all. So in this case, we're going to be really using the write, and you know, our arguments go to R0, R1, and R2, and then we'll be doing a sysexit, which we need only R0 for our argument. Or actually, we don't even need that. There's really no argument. That's just the return value. So we just need to define that it's exit. All right, so let's go over to our terminal again, and we're kind of going to just set up a skeleton of what our program is going to look like and fill it in with binary. So we're going to go ahead and just call it hello. And we're just going to kind of type in all the stuff we need for the most basic assembly program here. Okay, and then our instructions will go here in the middle. You'll note that if you do a lot of assembly, I put the string in the text section. I didn't make a data section. I know that's kind of wrong. In this case, it actually makes it kind of easier because although I called it string, I gave it a label of string. We can't actually use the label in our assembly instructions because that's assembly shit, right? So being that we're doing it all in binary, we actually have to know the address. We can't just use string and it translates the address. We don't have that high-level ability of assembly language. So we'll get to that, but this actually makes it easier for us to access that address. I mean, we could do it with the data section, but it'd be harder. It'd be a completely different memory area. So let's get started by, I'm just going to write some pseudocode here. So our first thing was we needed to do a write instruction. So we're going to have to be moving into R7 the value 4, and that is because that's the syscall number, right? And this is definitely not assembly right here. This is not the format of assembly language, and I'm doing that on purpose because I'm avoiding using assembly altogether. So then the next thing is our first argument for what kind of file descriptor it is, which is standard out. So we're going to, in R0, we're going to be putting the number 1 in there. And then our next argument goes into R1. That's the pointer of where this hello world is. So this is the trick we're going to do. We're going to put PC in there. PC is the address of our current instruction plus a few bytes. So we got that as a point of reference, and then all we need to do is add to it the amount of instructions that come after. So in this case, I'm going to add to R1, and for now I'm just going to say some number. We'll figure that out in a second, what that offset's going to be. And then moving on, our final argument to this write is going to be how many bytes the string is, and that's 12 bytes, including the carriage return. And after that, we just need to do our syscall. Then also we need to exit gracefully, so we're gonna, in R7 for our syscall number, we're going to put in the number 1, because that's the number for exit, number 1. And then we just need to do the syscall again, and that's it. That's gonna be kind of the guideline of what we want our program to look like. And then in this case, I'll go up to the number and fill that in. Being that each instruction is 32 bytes, I mean, not 32 bits, so 4 bytes, and we have 4 instructions after this, we'll just put in 16, and it works. Even though I'm kind of simplifying it to say that, you know, you can just count the 4 instructions below, and that's the offset, you know, 4 instructions, one instruction being 4 bytes times 4. It's not that simple, but it works out in this way. So now all we need to do is write this program in binary, which is kind of cool. AS, the assembler AS has this, NASM has this, but really we need to be using AS. And the way to do that is we say we want to do a word, which is going to be 32 bits, and we're doing this prefix of OB, which means what is to follow is going to be binary. So our first instruction, we're going to use the Atlas. It needs to be a move instruction, and specifically it's going to be of the immediate form, not register form. I mean, even though, you know, you see it goes into register, it's really talking about what's going into it. In this case, it's just an immediate value, a number, as opposed to this third instruction here, it's a register going into the register. So we just need to do an immediate form. Go to the Atlas, this big Atlas here, and I'm going to go over to where those kind of instructions are that we need. Zooming in. So data processing, immediate. And we need to do a move, which we scroll down, and here's our move immediate. Make that bigger. And here we have it. Those are how we need to do the ones and zeros here. First thing is the condition field. So I'll scroll over and we'll get that out there. I'm doing the 1110. That's for unconditional instruction, or no conditions, none conditions. And I'm going to put spaces. We're going to get rid of them later, but I'm not doing the spaces. I mean, I am doing the spaces now. So for this, we have 001, which is defining that we're in our data instructions for immediate values. And for move itself, it's 1101. So we'll do 1101. And then we have whether we want to set the flag fields or not. It doesn't matter what we put in here, but I'm going to do 0 because we really don't care. And then we have the gray bits here, the don't care bits. It really doesn't matter what we put in here, but we'll take the suggestion for this instruction. And this is the destination register where we want to put the value. And in this case, it's 7, R7. And it really is as simple as putting 7 in binary. It's 7 in binary. And then our immediate value, our 12-bit immediate value, which for larger values, it's a little bit more complicated because it's not just a straight 12 bits of binary. There's another kind of subfield that can multiply the values out, but for smaller values, it works pretty literally. So we're trying to move the number 4 in there. So it's 12 bits, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and that's 4. All right, so that's an instruction. We're going to move on to the next one, which is very similar format, just different register, different value we're putting into it. So we can kind of cannibalize the one above it. So that was our condition. It's the immediate form. It's going to be a move, not setting the fields. And these bits, like I said, don't even matter. Those are the don't care bits. So fuck it, put in ones because we can. And this is going to be R0, so that's all zeros right there. And then the number 1 in binary for the immediate number we're putting into that register. Now we're going to do the register form of the move instruction. It's a little bit different. That condition field is always that first field right there. So now we're going to zoom out a little bit, come over here, and this is where our register version is of these instructions. So we scroll down till we get to the move. So this move register, so those first machine bits are going to be zeros, 3 zeros, instead of 001, you see. And then being that it's move, it's 1101 for the instruction itself. And you notice the pattern there, it's the same as above. It's just the only difference is we're doing register instead of immediate, and that's this up here is what defines that, the 000 instead of 001. The S bit, going to do the same thing, and then the next field is going to be our don't care bits, so really don't care. I'm going to do 0, it doesn't really matter. And then our next bit is the destination, which in this case is going to be our 1. So in binary we do 1. And then our next field after that is going to be 8 machine zeros. So 1, 2, 3, 4, 5, 6, 7, 8. And then lastly is going to be our field for the register that we're trying to copy into the destination register. And in this case we're doing PC. PC happens to be all 1s. So we have that. And I think before I said we needed to add register 1. I don't know why I typed move. It's add. My bad. So we're going to blast out this instruction, note conditions, and it's going to be immediate form. So we'll pop out of here, and immediate form of add is right here. I know I am flying around a little bit, but once you get familiar with the Atlas, you kind of get the idea of where things are. And there's helpful little icons here for adding. So anyway, we do our condition, we do 0, 0, 1. And for add is 0, 1, 0, 0. Our next field is the flag, which we're not setting. I mean, we could for an add, but we're not doing something conditional after that, so it doesn't matter. And then what we want to do is we need to add this immediate value to whatever's in Rn and store it in Rd, which is kind of different than x86. Normally you only need 2 operands. Here it seems like we have 3, but really you do have 2 operands, and then you have another register for where the sum goes into, which is a little different. So in this case, our first one is the register, one of the registers we're using to add. In this case, it's register 1. And then we also want it to go back into register 1 when we're done, and then we're putting 16 into our 12-bit value. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that would make it 16 right there. So now, our next argument, we need to tell our Linux guy here that the string is going to be 12 bytes long, hello world, including the carriage return. So condition being none. This is going to be an immediate form, so that's the version for immediate. It's move, and I mean, yeah, I'm not looking at the table, but you kind of can cannibalize what you see above once you get an idea of this. I mean, if you're going to do this yourself, you could probably look at the Atlas a little bit more, but I've done this a bit, so it's kind of in my head. The next part is the don't care bits, so don't care. And then this is the register I want the value to go into, which is 2 for R2. And then we want 12 for immediate value, which is that. And then we need to do a syscall. And in assembly, this is generally called SVC, used to be called SWI, whatever. I don't even know. I don't care because I don't have to write the assembly. I just look at it in the Atlas and type the binary that I need. So in this case, it's the condition. I don't even need to look at the Atlas for that. I know the condition is going to be none. And then let's zoom out here and look for that instruction, which is going to be right here. SVC, previously SWI, which is what it says in the manual, even though if looking at other people's assembly, they typically type SWI. I don't know, don't care, don't have to deal with it. So we got our condition. Then our next 4 bits are going to be 1s. So 1, 1, 1, 1. And then an immediate 24-bit value. And in this case, we're just doing 0. We're doing a syscall 0. That's just how it's done. So 24 bits of zeros. Cool. Now we got that. So that's our write. We did the writing. Now we just need to exit gracefully. So we need to put 1 into R7, which is our argument for which syscall to do. No conditions, and I'm going to just cannibalize instructions I have above. So it's immediate, move, not setting the field, can make this whatever. It's going to be R7, and then putting the value 1 in there. So finally, our last syscall to actually make it exit. I'm just going to cannibalize the syscall above it. It's literally the same thing. And there you have it. There's kind of our instructions so far. Although I'm going to kind of clean it up, I'm going to remove these comments and I'm going to get rid of all the spaces because we can't have those. And there we have it. We have our program in ones and zeros. I mean, the instructions part of it. That's it. Just pure ones and zeros. So we're going to save this. And then we're going to assemble it with AS. Output hello.o for object that we can then feed to the linker LD. So hello.o, and then we're going to output the name hello. Let's go ahead and try to run it. Hello world. There you have it.